Hi, everyone. Thanks for tuning in. Today, we will be talking about decision-making in artificial and natural systems. And today, we'll be talking with Dr. Ted Pavlic from Arizona State University. Thank you for joining us today, Ted.
Oh, thanks for inviting me.
And it seems like we have a lot of information to discuss in a pretty short time period. So what I'd like to do is just if you could quickly start by telling us a little bit about your educational background, where you went to undergrad and graduate work, what types of problems you were addressing at kind of each stage of your educational background.
Sure, yeah. So I actually originally was a software engineer for about, say, 10 years. I worked in, and this is before undergrad. So this is, I did a lot of internet work back before that was kind of a trendy thing to do. I did work on what some people might know as the Linux virtual server projects. I worked in, I set up one of sort of the largest LVS clusters. And after all that sort of software work, decided I wanted to go into undergrad into electrical engineering. And so I went to Ohio State University, which I think you're familiar with. And, yes. And I studied electrical engineering. I specialized in electromagnetics. I was convinced I was going to become an antenna designer. Then I got introduced to
what designer?
An antenna designer. So
okay.
like, you know, for cell phones and things like that. And but then I got introduced into what we call analog electronics, and that gave me the opportunity to get exposed to a much more sort of abstract field of electrical engineering known as control theory, which is sort of it fits within sort of a larger group of systems theory, which a lot of people sort of use, but there's a particular spin that sort of electrical engineers have. And so then I decided that I wanted to go into grad school for control theory, and I was shopping around for different grad programs, but then actually, sort of fortunately enough, I suppose, at Ohio State, there was a faculty member named Kevin Passano, who I walked into his office just to sort of talk to him about options for control theory, and I saw a lot of textbooks.
Before we get too far, so most of the last few speakers that have come in have been more from a psychology background.
Right.
Can you tell us a little, just very, very briefly, what is control theory?
Yeah, okay, so good question. So control theory, this is kind of it's sort of a broad topic. If the sort of prototypical example that you get in sort of a undergraduate level homework problem is the controller that controls the heat in a room. You know, it's a thermostat. It measures the temperature and it turns on and off your heating or cooling in order to regulate the temperature. More sophisticated examples of classical control problems involve when a pilot in a plane decides to turn the plane a particular way. There's a control system which moves the actuators in that plane in order to guarantee that it does what the pilot wants it to do. So it tracks the pilot's reference. And so things have gotten a little more sophisticated now, because when we look at control theory, I mean, you can imagine them not only in sort of the very mechanical sense, where you're designing, you know, what cable to tug inside an airplane, but even in sort of the social sense. So can I model a social system with inputs and outputs, and with that model figure out how to create a feedback circuit, measuring the output and changing the inputs, so that maybe I can actually control a mass group of people, or things more, you know, something in between. If I have a mass group of robots that are sort of doing their own thing, rather than controlling them individually, how can I adjust their constraints so they do as a group what I want them to do without me having to download new software to them, things like that. Okay. So that was kind of good. And so because there's feedback involved in there, there's a lot of things involving stability and things like that. You can't just say that I'm going to make the input some function of the output and then have it snap into place. And so that's where kind of the math comes into play, these real analysis stuff. And so what interested me when I met Professor Passano is that so on the side, I was very interested in biology, but it was purely recreational. I was reading a lot of books on the subject. Some of them were more academic than others. A lot of them were very popular. But I saw on Passano's shelves, he had all the same books that I was reading, plus all the control books. And I found out that he was looking to animals to sort of understand how feedback laws are implemented inside an intelligent agent that is subjected to a complex environment out in nature, and he's doing bio-inspired design. And that's kind of where I got started in the field that I've kind of been working in since. So we sort of started out looking at solitary animals and how they foraged, and how we could take those insights and build autonomous urban vehicles, autonomous ground vehicles, autonomous air vehicles for a number of different contexts, military, reconnaissance, otherwise, that acted like these animals, and then graduated up to sort of the social level. So how can we look at cooperative breeding in fish and figure out how to redesign power systems and how they distribute power around a grid? How can we then look at ant colonies and figure out how to move energy flows around a building in the built environment?
Can you provide a little bit more specific example? So, like, what about ants and the way they move, the way they travel, communicate? What did you model? What aspect of this, of the ants, either at the individual level or at the group level?
Right. So we do quite a bit of that at both levels. So I mean, it's like, for example. So many good examples. So one sort of easy example at kind of the group level is that an ant colony, by the way, I'm getting a little bit of feedback now. I don't know if volume's changed over there. But so it's been determined over the last, say, 20, 30 years by a guy named Steve Simpson and another guy, David Raubenheimer, that if you give any animal, a solitary animal, a dish of protein, high protein food and low carbohydrate food, and a dish of high carbohydrate food and low protein food, and just let them mix however they'd like, and then measure how much protein and carbohydrate they bring in, the animal will end up regulating to species-specific targets for both protein and carbohydrate. So larger animals eat more, but they still have the same ratio of protein and carbohydrate. The interesting thing is now, we figured out that if you give ant colonies the same choices, at the colony level, they regulate to these species-specific targets. Somehow, the colonies are organizing themselves so that the protein foragers can adjust for whatever protein and carbohydrate foragers are bringing in, and vice versa. And it turns out this maps very well onto the problem of, say, intelligent lighting. If you have a bunch of lights overhead and a couple of sensors at the level where you're sitting, you need to figure out how to allocate power to different lights so that you can get all of these different sensor constraints met, and try to do it in a very decentralized way. And we found a way to get insights from ants to solve that problem, and then also then how to take new lines of inquiry, how engineers think about that problem, and investigate potential problems that ants and honeybees could be having in like normal agricultural policy. So that's kind of an example of how we go back and forth.
So are you still getting feedback? Sorry, I had to turn the volume down quite a bit on this side. Are you still getting feedback at all or no?
Yeah, unfortunately, I'm still getting feedback. So it feels about the same as it was. So if it's easier to turn the volume up, I might as well turn it down.
Okay. So very interesting. So again, you're the first person that I've brought in lately that's talking about decision making, for example, coming from like an ecology engineering perspective. Everybody else has been attacking it from psychology. How has kind of psychology influenced your line of research?
Okay, so as maybe a good example, I'm going to talk about some research that was done in. I currently am about to start a position in engineering here at ASU, but I currently am sitting as a research scientist in the lab of Stephen Pratt, and a recent graduate, Stephen Sasaki, did a lot of the work that I'm about to talk about here. And so Taka was very interested in the psychology of a colony. And so what he would do is give colonies and individuals decision-making tasks, compare how they would do, and then try to figure out how the colonies were getting rid of these sort of individual level cognitive illusions and cognitive decision-making problems. As a simple example, we can give a colony two nests. One of them that we know that the colony is a good colony nest, so colonies always will pick it. The other one we know is a bad colony nest. We know they'll never pick it. And we can then measure things like how long it takes them to make their choices and just how well they make the choice. If we only give them two nests, good and bad, and we give that to an individual, that individual will always move all of the brood we've given her into the good nest. She always chooses the good nest. But if we give her 4 good nests and 4 bad nests, then it goes back to 50-50. So in that case, now that she's faced with 8 opportunities, even though it should be the same choice, it's you know, just as many good as bad, but she basically what performs that chance. But if you give the colony that same 2 sets, they always pick a good nest in either case, and they do it so fast that no individual within the colony actually sees any more than 1 nest. So there's some aggregation phenomenon inside that's able to prevent this cognitive overloading that happens at the individual level from scaling to the group level. And it would be great from an engineering point of view if we could sort of design that to some artificial agents so we could build them very cheaply at the individual level using some heuristic that's sort of easily short-circuited by the environment. But then when we put a bunch of them together, all of that gets washed out and they do the rational thing. So that's sort of one example. And there's many, but I'll just leave it there for now.
So I want to make sure the audio is kind of cutting in and out for you, so I want to make sure that I understood. So if you give, for example, an ant has to make a decision between 2 items, the ant's pretty good at selecting the better alternative. But when you increase the number of items, so let's say you have 4 good items, or 4 good choices and 4 bad choices, now all of a sudden the single ant has trouble making this distinction and starts responding like at chance performance. But at the group level, the group somehow is able to make the better decision. Is that correct?
That's correct, and they can make it even though no individual has seen more than 1 nest.
So would you be willing or interested in speculating on how they're able to communicate or do this? Do you have any, is there any idea how they do this?
Well, so these particular ants, a lot of people when they hear about ant decision making, they immediately think about trail laying behavior. This is very popularized, that there are certain ants that lay pheromone trails to a particular site and it gets positively reinforced and it's like a spatial memory. These ants don't do that. Our ants, an individual will go from an old nest to a new nest. She'll come back to the old nest and then she leads what's known as a tandem run. So she'll be able to recruit a single individual to follow her, and they go in a stepwise process where the leader will walk ahead of 2 steps, stop. The follower will then follow up behind her, touch her on her rear end with her antennae, meanwhile while scanning left and right. And then the leader will then repeat this process until they both finally reach the destination, at which point they can break off this partnership and then come back even on a different direction. Now, eventually what happens is that the ants determine there's sort of a quorum that's been met at the new nest. And when they come back, instead of leading a tandem run, they actually pick up their other nestmates on the's backs and run with them to the new nest. So they carry all their nestmates with them. And you say, well, then where's the symmetry? How's the symmetry being broken? Well, it turns out that the probability of leading a tandem run scales with the quality of the nest. And so this is a decentralized distributed decision-making process, sort of analogous to some of the neural models you have of how sort of like neurons break deadlocks. And we think that we don't know all of the details, but we think that the dynamic properties of this process is what allows them to aggregate information like this. They're effectively storing memory in the nest as opposed to in the individual agent.
Fascinating. So what types of things, knowing this, how could you start building this into, like, can you talk a little bit about your research using, for example, what we know about ants or honeybees and how you've taken insights from that and used it to, for example, create algorithms that can make decisions and so on? How have you used this insight from like ecology to building algorithms?
Right. Well, so things like the intelligent lighting example I gave earlier, the insight there is that, so in the past, when people solved these problems, they would put a lot of computational intelligence in the light, and the sensors were just dumb feedback from the environment. What we've sort of learned is that ants typically make use of the environment. So they look at quorums that are actually out in, so it's as if, you know, and honeybees do this too. If you have multiple choices, rather than each individual keeping track of the choices, they leave individuals at the site to sort of a vote. And so they're modifying the environment, which affects the future decision-making of the future ants. And so we thought, you know, we've been looking for ways in which we can use the environment in other sorts of ways. So in the lighting case, we actually put all the intelligence on the sensors, and we use the light itself in the background as an environmental cue, which naturally synchronizes the sensors, even though they don't communicate with each other directly. So that's kind of one example. A totally different example is, periodically we do think about human cases. So how can you design sort of better technological interventions to sort of improve human decision making? If you were to think about sort of Amazon.com, every review is kind of like a trail that an ant has led. One person leaves it, it then gets read by someone else who might buy the product, who might reinforce it, and you get a lot of positive feedback. But that review stays there. If a new product comes into play, then there's no way for that product to really get an edge, or it's very difficult for that product to get an edge. Now, trailing ants, you have the exact same problem. If you give them a really good feeder and then a bad feeder, they'll pick the good feeder, they'll get a trail going to it, but then if you switch it in the middle of the experiment, they don't change. I mean, there's some ants that have figured out how to change, but it's a much slower process. Whereas our tandem running ants, they track back and forth, no problem. Imagine if Amazon, each review, after say 5 people read the review, it disappeared. Now the reviewer who took the time to make the review, that might be kind of off-putting to them, but it would totally change the dynamics of how products are ranked and recruited to in these sort of human systems like Amazon. So, you know, how can we learn from the ants to sort of build technologies to change group level decision making in humans? That's another sort of important part of research we're doing.
Fascinating. So I have a question. What is like statistical mechanics, and how does it contribute to our understanding of like emergent behaviors?
Great. So yeah, so a lot of times when we look down at these ants, we're looking at, you know, hundreds of individuals. You know, and we talk about the actual colonies can be much larger, but if you look at the ones making decisions that are focal to us, you know, we're talking about, you know, tens to hundreds of individuals. And sometimes they're doing something that it isn't necessarily a decision task. It's you know, how do you allocate around a load that you want to carry collectively as a team back to your nest? And in these cases, there's clear sort of macroscopic variables like the speed of the load. It tends to be regulated. It goes pretty constantly back to the nest. Meanwhile, these microscopic properties, like the ants connected to the load, pop on and off. They change a whole bunch. Now, we can measure these microscopic properties and sort of statistically capture characteristics of individual ant behavior. And then we can use these properties, I'll say these methods from statistical mechanics that are able to sort of scale up from, you know, a bunch of molecules bouncing around a room to coarse-grained variables like temperature and heat and density. You can say, well, how do we scale from individual level parameters to group level behaviors that we might be interested in understanding, or in the engineering case, designing? And it very often turns into something that looks like a mechanical engineer's homework. We might do a design problem at the macroscopic level, and then that gives us parameters that we can input into a swarm of robots, or we can assume we can take a hypothesis about the individual behavior, project the macroscopic variables that we can observe, and then compare them to macroscopic variables we have observed and falsify that individual level behavior. So that's kind of how this multi-scale modeling fits into it.
So I want to switch the topics here. So you've been recently collaborating with some theoretical physicists on information theory and how it may contribute to our understanding of the origin of life. It seems completely different. Can you comment on this, and how does it tie into the rest of your work?
Yeah, absolutely. So, there's a cosmologist who's done actually quite a bit of work in the origins of time, and the origins of the universe in general. Paul Davies, who works here at ASU, and he has a colleague here, Sarah Murray Walker, and they basically, the quote they give me is that, we figured out the origin of the universe. Now we need to worry about the hard problems, the origin of life, and so their perspective is that when you look at a bunch of kind of biochemistry, a bunch of these particles that don't really have any agency bumping around into each other around the origin of life, information should have gained some causal efficacy. In other words, these particles' actions should have become coupled in a way that started to be adaptive. They started to adapt to their environment, started to react to their environment. And we're trying to understand the fundamentals of how does information go from being something that's a derivative property to being something that is causal. And so they actually approached us because we looked at ants, and ant decision making as a great model for this. So whereas we observe the contributions to individual sort of macromolecules, biochemistry reactions, we might be able to actually model the individual contributions of an ant in a very similar decision-making process and learn fundamentals about how information is stored, processed, and transferred in nature, and then scale those actually down to the level of these biochemical aggregates, and even go even farther. We've actually found some macromolecules that have conditional behavior. They're plastic. Depending on their environment, their conformation changes, which changes how likely they are to react with other elements of the environment. So this is sort of a new area of behavioral chemistry. And so, studying animal behavior may be able to scale down to extremely small levels and then scale up to these artificial systems. So, and it might be the same fundamentals at all levels.
Great. We're running out of time. I'd like to hear a little bit about, continue with what you're doing more recently. You're organizing a conference, correct? The 2015 Conference of Complex Systems, is that correct?
That's correct. I'm on the local organizing committee. It'll be held here at ASU.
So what is this conference about? What types of things would we expect to see at this conference?
Right. So this conference was actually originally the European Conference on Complex Systems, but this year they're going global and coming over here to the States, and so we're hoping to get a lot of the European crowd plus maybe a lot of the new crowd. So this community, this complex systems community, is sort of generally interested in systems which are irreducibly complex. So they have a lot of individual level components that operate with very simple rules, but have interactions which are really focal. And so if you take an individual out, all of the interesting properties that you were interested in just dissipate off. So you really need to analyze them as a group. That's where this sort of complex systems comes into part. And there's I think 6 or 7 different tracks. We've got everything from the foundations of complex systems to information communication technologies. We have biological complexity, socio-ecological systems, economics, finance. I mean, you can imagine not only are we interested in how groups of ants are adaptive, but we're also interested in how, say, groups of people participating in the stock market can contribute to a collapse. So both of these things are sort of can be analyzed with this complex systems framework, and these are the types of things I'll discuss at the conference.
All right, and you also just created the help organizer set up the Center for BioMimicry at Arizona State. Can you tell us about this center?
Right. So we have a new center for BioMimicry. We're a formal partnership with a group called BioMimicry 3.8. So BioMimicry has kind of several definitions. The group that we've partnered with, which is sort of a consultancy that previously has done a lot of kind of educational work on their own, that's now being formalized through ASU to sort of reach a broader audience. But they also work directly with companies who say that, they have a problem and they're interested in finding if nature has also worked to solve that problem. And if you can find a solution that nature's come up with, then perhaps it's going to naturally be sustainable. what we're interested in is not only that, we think that's great, but then also expanding that to just sort of look at how we can put these interdisciplinary groups together that can learn about sort of use biology as a challenge to sort of say, what new models can we come up with that can be useful in the engineering and design space, learning from biology, but also just sort of learning about how to think about these interesting systems from systems that have already been put together. And the center will hopefully foster a lot of these activities here at ASU, and then starting here at ASU, but then hopefully getting a little more visibility and then bringing in collaborations from elsewhere as well.
Okay, excellent. So what would be the best, if I want to learn more about your research, what's the best way to reach out and learn about your recent and past research findings?
Well, so you can try my website, which I think is in the lower third, tedpavlic.com. It's a good place to start. And then if you go to pubs.tedpavlic.com, you can see some of their publications. But there's a lot of new stuff going on. I'm starting a new lab here in August, and we're moving in several different directions. It's an engineering lab, but I'll still have ants in the laboratory. So I encourage people, if they're interested, to reach out to me. Check out my Twitter, Ted Pavlic, @TedPavlic. My Google Plus, I post a lot there. And so as more comes, we'll be posting it there. And I'm very interested in talking to people, hearing their questions, and hearing if they have any great ideas that we can help pursue.
And I have kind of more of a general question. I don't know how you want to answer it. So one is just kind of, where do you see your research really maps on closely with the interdisciplinary field of cognitive science, your understanding of decision making? You're taking a very interdisciplinary approach, engineering, psychology, ecology. So you really, where do you see this field going? Interesting questions in this interdisciplinary area. Or how should students get involved in this type of research? If I'm interested in pursuing a degree or going into cognitive science, coming at it from your perspective with an engineering perspective, how would you see them moving forward? So I guess it's kind of two questions. How do you see the field moving? What are the interesting areas that need to be addressed? And what's the best way for students to move forward to get at this?
Yeah, so those are kind of hard questions. So what I really like about cognitive science is that it's humans are an interesting animal to learn from as well. They can do so well at so many things and so poorly at so many other things. And I love some of these experiments in cognitive science that can kind of help quantify and describe these aspects of human behavior. And then when it takes from the engineering and the ecological side of view, then we can start asking sort of more questions that almost sound a little bit more evolutionary. Are these behaviors adaptive? Are they maladaptive to the particular scenario that they were sort of found in? And then are there sort of fundamentals? So for example, there's a guy, again, I'm very familiar with at OSU, this Roger Ratcliffe, who's formed these drift diffusion models that sort of really well characterize the temporal and accuracy characteristics of decision making in these two choice tasks. And what we've strangely found,
too, correct?
Yeah, exactly. What we've strangely found is our individual ants, we can force them to make these two choice tasks as well, and they're modeled really well by this exact same framework. They operate very quickly at easy decisions. They take tenfold more time to make very difficult decisions, and the shape, it all fits. But what we're finding is that we're not entirely sure that this is being driven by processes inside. And so people like Deborah Gordon have also found very similar things like this, but they use leaky accumulator models as opposed to the drift diffusion models. But similar idea. But the strange thing is that we're not quite sure if this is being driven by some sort of neuronal process inside the ant, or some sort of actually statistical mechanical process that's involved with the ant and its environment. Now, let's say we can get this exact same process from the ant responding to its environment, then that sort of suggests that maybe there's new investigations people could make in cognitive science to say that perhaps that some of the characteristics that we think are intrinsic to humans actually are emergent properties of humans and their environment, just like they are in the ant case. And so that would be, a great direction that I think it needs a lot of sort of help from, I think, both sides, or in fact, maybe all three sides, because very often to test these things, we have to build artificial systems that we can subject to more cases that we can with the ants. Humans are actually sometimes easier to experiment with for these types of tests than you are to, it's hard to force an ant to make a decision, but it's easy to force sort of a robotic ant to make a decision. So I think all three could play together in sort of understanding where these characterizations come from. Are there fundamentals there? And if there aren't, can we use them to sort of build new heuristics to do design or analysis or all sorts of things? Does that sort of get at what you were hoping for?
Yeah, definitely. And are there any advice for students that may be interested in pursuing a similar line of research?
Yeah, well, so interdisciplinary research is difficult. I would say, be persistent.
That's where the field's going, though. I mean, that's where, when you look at what the projects that are being funded, these are the really big interdisciplinary projects that are more likely to be funded.
Yeah, it's true that there are definitely funding opportunities, but you have to look at whether those funding opportunities intend for those to be multi-investigator, very collaborative projects, or if they're going to be amenable for sort of a bunch of already multi-interdisciplinary people coming together who are just sort of good thinkers on these things. And despite the funding opportunities, being able to get into positions to do the research can be very difficult. I mean, in order to sort of get noticed by hiring committees, you very often need to have a presence in a discipline, and those hiring committees come from more traditional disciplinary boundaries. And so that means you've really got to work on keeping your representation up in the multiple disciplines you want to work in. And this is something that I didn't quite understand as a grad student, and it really hurt me very early. And I've gotten a couple of lucky breaks, and things are picking up now, and I understand it a lot more. But nobody was around to sort of explain this to me. And I guess that's what I'd say is if the more interdisciplinary you get, make sure you've got plan Bs, make sure that you can still call yourself a strong something. You can call yourself two strong somethings if you can, that'd be great, but at least have something so that somebody's gonna be able to recognize you, so they'll actually be able to hire you in the long run, so that you can then keep doing these multidisciplinary things that if you would have just sort of only done, then maybe you would have been too thinly spread for people to notice.
I think it's excellent advice. I just wanted to thank you again for chatting with us about your research. And if you have more questions, or if you have questions at all, feel free to post them on the event post. And thanks a lot. Thanks, Ted.
Thank you.